Unitree released a humanoid robot named Superman that runs faster than Usain Bolt and jumps 2 meters from a standing position. The robot achieved 12.66 meters per second, surpassing Bolt's peak speed of 12.42 meters per second during his world record run. Superman's legs measure only 0.85 meters long, meaning it generates speed through actuator power and leg cycling frequency rather than stride length. The robot cleared a 2-meter standing vertical jump while maintaining balance upon landing, a control problem that demands sophisticated coordination. These performance metrics come from company demonstrations and remain unaudited, released 1 week before Unitree's Shanghai IPO trading begins. Unitree raised approximately $905 million in its IPO, with retail demand exceeding 8,000 times oversubscription, a Shanghai record. The company operates from Hangzhou, and founder Wang Xingxing attended a technology summit hosted by President Xi Jinping last year. Major investors in Unitree include Tencent, Alibaba, and DeepSeek, positioning the company at the center of Chinese tech advancement. Unitree produced and delivered approximately 18,000 bipedal humanoid robots across multiple models as of July 2026. In the first half of 2026, Unitree shipped 5,900 humanoids, up 170% year-on-year, representing 31% of global humanoid shipments. Chinese vendors accounted for more than 97% of global humanoid robot shipments in the first half of 2026. In April, Unitree's H1 humanoid achieved 10.1 meters per second on an athletics track, though the company flagged possible measurement error. The H1 has human-like proportions in its thighs and calves at 80 centimeters combined length and weighs approximately 62 kilos. Wang Xingxing predicted humanoids would exceed human sprint speeds by mid-2026, attributing this to cheaper components and improved algorithms. Performance records function as stress tests, loading all hardware, software, balance control, and body coordination simultaneously to identify failure points. A robot capable of landing a 2-meter jump has solved movement problems necessary for traversing rubble and rough terrain. Mastering dynamic movement enables humanoids to eventually operate in disaster response, rough terrain, and hazardous environments effectively. Performance records do not guarantee deployment. Reliability, stability, and real-world adaptability present separate and significantly harder challenges. 23 humanoid teams competed in a simulated firefighting and rescue mission at the World Humanoid Robot Games in Beijing. The organizers ran the event at an actual fire brigade instead of a controlled indoor mock-up, with human firefighters monitoring robot performance. Each robot completed 3 randomized tasks: identify hazardous substances, locate and close valves, and operate a fire extinguisher. Only 3 of 12 teams that competed on Sunday completed the full challenge, demonstrating the difficulty of real-world deployment. Unix AI's robot finished within the time limit, but moved slower than a human firefighter and required 2 attempts to align with the extinguisher. Rain, shifting outdoor light, and environmental unpredictability degraded robot visual recognition and manipulation capabilities during the competition. Failures in perception or motion planning caused entire mission failures, as robots had to identify objects, plan actions, and coordinate joints simultaneously outdoors. Different tasks require opposite hardware characteristics. High-precision joints for delicate work conflict with high-torque actuators for strength and locomotion. Some teams equipped robots with omnidirectional wheels instead of feet, while others prioritized multi-jointed hands for fine manipulation tasks. Many teams used China-developed joint modules, with servo actuators ranging from low-force precision control to high-force movement capabilities. Teleoperation with VR headsets remained essential, with operators receiving first-person camera feeds and steering robots in real time during competition runs. The World Humanoid Robot Games expanded from 3 days to 5 days, with sessions running afternoon and evening throughout the week. The competition grew to include 30 competitive events, plus 21 scenario-based challenges, up from 26 total events at the inaugural edition. New competitive additions include long jump, weightlifting, tug-of-war, and table tennis, expanding the physical demands tested. 2,056 robots from 666 teams across 16 countries participated in the expanded games, with team participation up 138%. Robot participation quadrupled compared to the inaugural games, creating exponentially larger datasets for failure analysis and system improvement. Every botched valve turn and misaligned gripper provides valuable failure data that feeds back into perception, motion planning, and AI development. Foundation Robotics proposes deploying humanoid robots called Phantom to monitor the U.S. southern border for terrain navigation and surveillance. CEO Sanket Pathak claims Foundation demonstrated its technology to Department of Homeland Security officials and holds discussions with national security agencies. The Department of Homeland Security states it currently has no agreements, pilots, or active prime contracts with Foundation Robotics. Foundation's Phantom humanoid is 8 meters tall, weighs 80 kilos, and features 29 degrees of freedom for terrain navigation. Phantom can autonomously navigate uneven ground, distinguish people from obstacles, map surroundings, and flag potential border crossings for human officers. Foundation proposes tunnel operation and continuous surveillance capability, while personnel maintain safer positions away from border risk areas. Phantom's top speed of 7 meters per second prioritizes endurance and carrying capacity over sprinting, with 40-kilo payload capability. Foundation's cycloidal actuators deliver up to 160 newton-meters of peak torque, with backdriving torque under 1 newton-meter. Actuators feature response time below 10 milliseconds, low backlash, and quiet operation, minimizing wear and maintenance for industrial and defense applications. Foundation's Cortex artificial intelligence fuses language, visual, and multimodal models with physics-informed AI using deep variational Bayes filters. Deep variational Bayes filters encode sensory data, update predictions through Bayesian inference, and generate actions based on expected outcomes. Foundation claims this approach requires less training data while providing better predictive power, adaptability, and generalization than reinforcement or imitation learning. Fijian Robotics released Phi-Zero, a cross-embodiment foundation model that preserves task knowledge when robot bodies are swapped. Normally, changing a robot requires significant retraining of intelligence systems, but Phi-Zero encodes physical structure and state to maintain knowledge transfer. Phi-Zero uses an embodiment graph covering morphology, sensing, actuation, state, environment interpretation, and action prediction capabilities. Fijian built 3 tendon-driven soft manipulators, nicknamed Doctor. Octopus arms with varying flexibility and payload capacity for real-world testing. The A01 model features 1 flexible segment, 2 degrees of freedom, and 750 grams weight with 200-gram payload capacity. The A02 steps up to 2 segments, 4 degrees of freedom and 400-gram payload, enabling more complex manipulation tasks. The A03 features 3 segments, 6 + 1 degrees of freedom, a 50-centimeter reach, and 600-gram carrying capacity. Soft arms present a harder test case than rigid joints because continuously bending shape changes as the arm works, complicating motion planning. Phi-Zero demonstrates one-shot learning by accepting a single human demonstration as context, extracting task intent without requiring additional training. The model extracts objects involved, task sequence, contact events, and desired end state, letting the robot solve execution with its own morphology. Fijian frames this as soft embodied intelligence, using specialized hardware bodies driven by generalist intelligence rather than single robots doing everything. This architectural approach means hardware no longer carries the entire burden of generality, enabling specialized machines for confined and hazardous spaces. These competing approaches represent a fundamental fork in robotics philosophy regarding how intelligence and embodiment should relate to each other. This week's developments reveal rapid advancement in robotics hardware and capability, but also expose persistent gaps between lab performance and real-world deployment. Don't forget to subscribe and turn on notifications to stay informed of the latest videos.